Hello friends, welcome to lecture 2 of digital signal processing. In this lecture we will study about the discrete time systems. So we will study about the various type of discrete time systems like memoryless system, linear system, time invariant system and causal system. Then we will understand about the stability of a discrete time system. So let's proceed. So discrete time systems. Discrete time systems. Okay, so first of all, how can we represent a discrete time system mathematically? So any system we can represent mathematically something like this. So for a this is specific to discrete time system. So where t can be any function. So as an example, it can be a scaling, it can be a delay. So if I have to represent it on a block diagram, it will be something like this. This is the input xn, this is in output yn. So for a discrete time system, output yn is related to input xn with a function which we can call as t. Example of this function t can be, let's assume, scaling, delay and so on. Okay, so now going further in this lecture, we will study about different type of systems, different types of discrete time systems. So let's study first about the memoryless system. So as we can understand from the name, a system which does not have any memory is memoryless system. Okay, or in other words, when the output yn depends on input xn at same n. Okay, when the output yn depends on the input xn for the same n. In this way we can say that this system is memoryless system. Okay, as an example, let's assume yn a square function. Okay, so in this case the output yn depends on input xn for the same value of n. For example, y of 0 is equals to x0 square, y of 3 is equals to x3 square. An example where the system is not memoryless is a delay function xn minus, let's say, 2. So here we can see that y of 2 is equals to x of 0. Okay, so here the output y2 is depending on input x0, so the n value is not same. So therefore this system is not memoryless, while this is. Okay. Now we will study about the linear systems. First of all, linear systems follows the principle of superposition. Okay, and we can decompose the principle of superposition in two steps. First, we can write mathematically it as where t is again a function, any function. This is equals to t individually and these are their corresponding outputs. So here they mean that if xn is an input to the system, yn is the output. Similarly, if x1n is the input, y1n is the output. If x2n is the input, y2n is the output. So this property, we can say this is an additive property. Okay. So next, the second one is if t of a xn is equals to a into t xn is equals to a into yn, where a is any arbitrary constant. Fine. This is nothing but scaling. Okay. What if we combine both of them? If we combine both of them, we can write this as let's say b, any other constant, okay. This is actually this relation we can comes from principle of superposition. Fine. Okay, so going forward we will focus on this relation. Now let's do some generalization to understand more about the linear systems. Okay. So let's assume that, let's write xn as a sum of multiple sequences. In this way, the output will be, we can write like this. So the point to understand here is that if this is fed to a linear system, this will be the output. Okay. Now let's take an example of a linear system. Let's take an example of accumulator. An accumulator you can write as yn equals to summation k minus infinity to n xn. Fine. Let's check whether this system is linear or not. Okay, so the way to check this is as follows. So first we will write y1n So first we will write individual system output for individual system input. So for when the input is x1n, the output is y1n, which we can write as this. Okay. When the input is x2n, the output is y2n. Okay, this is one part. The other part is, what if the input is x1n plus x2n? So okay, so what if the let's assume that there is another input x3n, which is x1n plus x2n. Okay, and x3n, when given to a linear system, the output is, let's assume, it's y3n. Okay, so we can write y3n as the same expression, k equals to minus infinity to n. So instead of xn, we will write x3n, and let's expand x3n as, okay, while doing their individual summation, x1n plus summation x2n. This is y3n. So here we can see that y3n is actually equal to y1n plus y2n. They both are equal. So y1n plus y2n is equals to y3n. Or in other words, when we gave x1n plus x2n as input, we got y1n plus y2n as output, which proves that this system is linear. Okay, cool. Now let's take an example where the system is not linear or non-linear. Okay. So let's take an example where the output Wn is log 10 mod of xn. Okay, where this is the input and this is the output. Okay. So one point here to understand is that if we have to prove a system not linear or non-linear, we just have to find one combination of inputs for which either the additive property is failing or the scaling property is failing. Okay. So let's take an example. Let's assume that x1n equals to 1. For this, w1n is 0. Fine, log 10 of 1 is 0. Let's take x2n equals to 10. For this, w2n is 1. Okay. Fine. So here we observe that x2n is equals to 10 times x1n. So if the system is linear, what we should have? We should have w2n equals to 10 times of w1n. Is it so? No. w2n is not equals to 10 times of w1n. Okay. So this system is non-linear. Cool. Now we will study about another system known as time invariant system. Time invariant system. So the statement about this system is time shift in input causes corresponding shift in output sequence. What does it mean? Let's say we have an input output combination like xn, yn, where this is the input and this is the output. We are shifting them by some delay. Let's say x1n is equals to xn minus n naught. So the corresponding output of this system when the input is x1n, if it is following the same equation or the same shift, whatever shift we are giving in input, the same shift is getting reproduced in the output. We can say that this system is time invariant. Okay, as an example, let's take again the accumulator system. Okay, what was the expression? Yn is equals to summation k equals to minus infinity to n xk. Okay, so here we will compute first if the input is x1n, let's say which is xn minus n naught. So y1n will be summation k equals to minus infinity to n x k minus n naught. Okay, cool. Let's replace k minus n naught by k1 here. What we will get? We will get k1 equals to minus infinity to n minus n naught x k1. Okay, now let's approach this problem from a different direction. Let's write what will be yn minus n naught. So we have to compute y1n, which we computed here. We have to compute yn minus n naught. So if both of them are equal, we can say that the system is time invariant. This will be n minus n naught xk. Are they equal? Match these expressions. Summation k or k1. These variables are dummy. So k equals to minus infinity to n minus n naught xk. k1 equals to minus infinity to n minus n naught xk1. Yes, they are equal. So the accumulator system is time invariant. Okay, let's now study a system which is time variant or not time invariant. Now let's study another example where the system is not time invariant or time variant, the compressor system, where the input output relation is this. Okay, so the first direction, that is calculating y1n when the input is xn minus n naught. Okay, so that will be simply. What about approaching this problem from other direction? yn minus n naught, that will be x. Okay, n minus mn naught. Are they equal? No. That means the system is not time invariant or time variant. Okay, cool. Now let's study about another system, causal system. Okay, so causal systems are the system where the output at n equals to n naught depends on input for n less than equals to n naught, or in other words the output does not depends on the future inputs. Cool. An example, let's say the delay system where the input is delayed by one sample. Okay, is it causal or not? Yes, it is causal. How? y1 is x0, y50 is x49, and so on. So yes, it is causal because the outputs are depending on only the previous input. The compressor system, what about this? Let's again take an example, or put the values here. y1 is equals to x2. The output at sample number 1 is depending on the input at sample number 2. So the output is depending on the future input. So it's not causal, or it's a non-causal system. Okay. So now let's study about the stability, or the stability of a discrete time system. Stability. So here we talk about stability in a BIBO manner. BIBO. This is bounded input, bounded output. What does it mean? That let's again assume that we have a system where the input is xn, output is yn. So the input is bounded by some value, let's say it bx, which is less than infinity. Similarly, the output is bounded by some value by. So if for a bounded input we have the bounded output, the system is stable. Very simple definition. As an example, let's assume a square function, or a system which is doing the square of the input. So there we can write okay. So the question is this BIBO stable? The answer is yes. So let's assume that our input is bounded input. So in that way, the maximum value of xn can be bx. Okay, so for the maximum value of input, the maximum value of output is bx square, or we can say that by equals to bx square. So if there exists a bx, there exists a by. So if the input is bounded, the output is also bounded. So yes, this system is stable. Okay, now let's take a look on a non-stable system. Yn equals to log 10 xn. Is it stable or not? The answer is no. If xn is 0, yn is minus infinity. So this system is not stable. Okay. So I would like to show you one more example which will be little bit more detailed. Again, the same accumulator function. Okay, you remember the expression of accumulator function is okay. So we have to find whether the system is stable or not. So let's work on this. So let's assume that xk is uk. Okay, so how it looks on time on a plot, something like this. This is n 0 1 2 3, these are all 1. So here we can say that my input is bounded by 1, so vx is 1. Now if we put this in this expression, the yn we can write as 0 when n is less than 0 and n plus 1 when n is non-negative. Okay, so we know that input is bounded, so we have to find whether the output is bounded or not. So the answer is no. So there is no finite choice for by such that n plus 1 is less than equals to by. Okay, so this accumulator system for this particular input is not stable. Okay, so till now we have studied, or we have talked about the properties of properties. So take a note that these properties are of systems, not of the inputs.